A 99% of life today is dwarfed by ancient insects.
99% of life today is dwarfed by ancient insects.
The modern eagle represents peak avian aerodynamics. Its wingspan can reach over 7 feet wide. And now, let's introduce the giant dragonfly, Meganeura. For this ancient predator possessed a wingspan up to 30 inches. And that's nearly the size of a modern crow or pigeon. Its wings were not feathered, but intricate networks of veins. These veins supported membranes far larger than anything today. And now that we understand the size, let's explore why. The secret lies in the atmospheric oxygen levels. During the Carboniferous period, oxygen concentration was much higher. This rich oxygen fueled gigantic arthropods like the Meganeura. Insects breathe via spiracles and trachea, a passive system. A higher atmospheric pressure allowed diffusion to reach larger bodies. Its massive eyes suggest keen predatory vision. Flight stability was a major biomechanical challenge for its size. Unlike birds, dragonflies use two pairs of wings independently. This allowed for unparalleled maneuverability and hovering capability. Modern insects are constrained by the square-cube law limitations. As size increases, mass increases faster than surface area. The Meganeura's immense body required powerful, fast-twitch muscles. The modern eagle relies on powerful, downward thrust from its wings. But the giant dragonfly likely relied more on sheer wing surface area. And now that we understand the physics, let's compare hunting styles. The eagle employs spectacular high-speed dives for prey captures. Its specialized talons are designed for grappling and securing large prey. A Meganeura, however, was likely an aerial ambush predator itself. Its formidable legs were equipped with grasping spines. It captured prey directly in flight, never needing to land. Sustaining such large wings in flight requires immense structural integrity. Fossil records confirm the sheer scale of these ancient flyers. The impressions reveal patterns, suggesting reinforced leading edges. But the modern eagle conserves energy by riding invisible thermal updrafts. A wing loading determines how much weight the wings must support. The lower air density of today makes such gigantism impossible. The eagle's landing is a marvel of control, feathered braking. The giant dragonfly likely struggled with precise, slow maneuvering. The eagle uses its beak for tearing apart substantial portions of meat. A Meganeura possessed powerful mandibles, suited for chewing insectile prey. It is a fascinating comparison across deep evolutionary time. Its vision was superior in detecting rapid motion across the field. The eagle scans vast distances with incredible visual acuity. A flight speed estimates for Meganeura suggest powerful, sustained cruising. The eagle achieves momentary speeds far exceeding the Dragonfly's cruise. A scale directly impacts the drag forces encountered during flight. The thin membrane was surprisingly resilient to tearing or tearing. Feathers offer flexibility and crucial instantaneous adjustments for the eagle. The heavy abdomen of the giant dragonfly required constant lift compensation. An endurance flight is a hallmark of the modern avian masters. The energetic ancient atmosphere likely demanded more continuous exertion. Now that we understand the mechanics, let's consider evolution's path. And as oxygen levels gradually dropped, insect size followed suit. Modern dragonflies are optimized for today's lower oxygen environment. But birds developed highly efficient one-way airflow breathing systems. This advanced respiration allows sustained high-altitude performance. One relied on atmospheric abundance, the other on biological refinement. The eagle represents the pinnacle of modern feathered flight design. A Meganeura reminds us that life's possibilities are environment dependent. But size is not always the ultimate measure of evolutionary success. And the skies evolved, and life adapted to conquer the new constraints.